Good afternoon, everyone. Thank you for coming to our tutorial today. We'd like to talk about the challenges in language model evaluation. With me, I have my co-speaker, Haley, and myself, Lintan. Both of us are from Eletheur AI. We are a non-profit open source AI research lab that works on interpretability, evaluations, and language models in general. So thank you again for coming to our tutorial. This tutorial is based on the experiences from the trenches of evaluation, where Haley and I are maintainers of the language model evaluation harness, which is used by, I believe, quite a number of people who like to make PR and issues daily. And this has kind of been a learning experience for us to kind of understand what is and what should be kind of like best practices in doing language model evaluation. This repository also happens to be like the back end for the open language model leaderboard that is by Hugging Face. And we've had experiences in reproducible evaluations, as well as seeing what can go horribly wrong when trying to reproduce certain evaluations that are described in a lot of these works. And so for this tutorial, we have this outline of, first we'll like to talk about like the fundamentals of language model evaluation. This is kind of like the tacit knowledge that seems to be everywhere, but at the same time it's kind of spread in multiple works, and I feel like it might be important for us to kind of talk about that before we then move on to like the specific evaluations, specific complications that happened on language models and what those complications are, how they arise when we want to evaluate these language models. Moving then to the benchmarking complications that talks about the challenges, but more from the benchmarking side. And then we close this tutorial by addressing what the pitfalls, what we can do today, as well as what future directions might look like. So the goal here is not to assume authority on what a benchmark is or what the evaluation should be like, but more of a, what are things to consider for at any individual works that, given certain challenges, what would work for certain cases, depending on what the context is. So we hope that you would leave this tutorial with knowledge about how language models can be performed, what these issues, what might be the best practices for reliable and reproducible evaluations, and what areas of future research would look like. So the scope here is more on instruction-based language models, instruction-tuned language models on zero or few-shot prompted tasks. So we won't necessarily be talking about agent evaluations or tool uses or retrieval augmented generation, more towards like the based and instruction tuning language models. So to open this tutorial, I'd like to motivate us with a key challenge that we find in language model evaluation, that being there can be many semantically equivalent but syntactically different ways of expressing the same idea. I think a good example here is how translating a source text, there can be many ways to paraphrase this and still convey the meaning clearly. However, the best tools to do these evaluations are actually the very models that we seek to evaluate. So there's not really a perfect way to evaluate correctness or an arbitrary natural language response, and therefore it really goes to like what case works best for what the context is. And hopefully that's what we can manage to deliver. So to start, I'd like to give the time to Haley to kind of explain about language model fundamentals.
Yeah, thank you so much, Lintang. Yeah, so to get started, we're going to try to sort of go back to the basics of language model evaluation and really walk through what people need to know in order to understand what is involved in doing language model evaluation correctly, and also what's involved in doing it incorrectly, or sort of what challenges need to be overcome. So to start off, just like first, why are we even evaluating these language models? There are a variety of reasons that we might want reliable evaluations. These could range from tracking progress in the field towards shared goals, like, say, improving models for image classification or question answering. And they let us sort of put a number to whether our models are getting stronger on these tasks and whether we've sort of solved them as a research community. And then evaluations are also importantly a quantitative measure of this progress. So an evaluation should be something that you could sort of strictly define, potentially in code, a process for getting a number of how well a model does a certain task on a sort of a standardized benchmark, where you can actually sort of compare certain models head to head and ensure that sort of the models of today are better than those for tomorrow. The models of today are better than those of yesterday. We also want to evaluate models when we want to try to make comparisons between methods. So we might present evaluations as proof that a certain method improves over a baseline. We might present evaluations when a language model, a new language model is released, trying to compare to competitors, and try and answer questions of basically what methods are better in what contexts. Evaluations are also useful just as sort of general sanity checks. So when we're training a language model, we might want to sort of progressively evaluate it as we continue through training to ensure that things are improving not just in the loss, but also that this is reflecting downstream performance. And we might also just want sort of evaluation data sets that we care about to run our models on them and sort of prevent regressions in performance when we're fine-tuning or compressing these models. So there are a variety of reasons we want to evaluate. And there are also many, many things that we want to be evaluating language models to do. Language models by design are meant to be sort of general systems where we might ask them to solve arithmetic questions, perform translation, answer factual questions, or complete code. And so all of these things need to be evaluated in a given model. And so we need to sort of design very diverse evaluations for these different downstream abilities. And so again, now just for a little bit of background to lay the groundwork for later, again, a language model is a probabilistic sequence model that basically will feed in some input text, and what we'll get out is a logic distribution, which is essentially for every token, which is essentially sort of a word in the language model's dictionary that it has access to, the model will produce a scalar valued score for each of these tokens. And so we can determine what the model's sort of guess for the next word will be by looking at these logits and picking the largest one. So in this case, when we feed in the model predicts cow as its output. And when we're training these models, we basically feed in a long string of tokens, and we do something called teacher forcing, which basically, when we feed in, say, these 4 tokens, at each different position, we will figure out what the logits for that model's prediction based on all of the previous tokens are, and determine what the model's choice of next token would have been. And in teacher forcing, what we'll do is we'll take these predictions, and instead of generating autoregressively by taking the prediction and feeding it forward and using it as the next word, if the model gets an incorrect guess, we'll just proceed as usual and use the actual token that we knew was next to sort of get a prediction at each point that can be easily turned into a probability distribution over next tokens. And so with this in mind, I'm going to try and talk about some of the sort of fundamental options that we have for interacting with language models when we're actually trying to sort of take a measurement from a model to observe some sort of latent capability on a given test example in a data set. And here we're going to just limit ourselves to sort of examples that involve only prompting and don't involve fine-tuning models. So there are 3 core settings that people evaluate models in. These are evaluating models' perplexities, evaluating them using conditional log likelihoods, and evaluating their ability to generate text. So I'll go through each of these in order. So the first of these, perplexity, is very similar to just taking the language modeling loss. It's also sometimes called things like rolling log likelihood. The way that it's calculated is for each, so given the model's logits output, when we feed in an piece of input data, we can get the basically model's prediction of the probability or log probability of some next token occurring given some previous tokens to condition on as the input. And so in perplexity, what we're going to do is if we have a data set of sequences that we tokenize, for each sequence, for each sequence in the data set and for each token in our sequence, we're going to figure out what the log probability of producing the actual next token in our data set would be. And we're going to sum these all up over our data set to calculate basically every token's log likelihood. and then just normalize by the total tokens in our data set. And this gives us basically the average likelihood the model assigns to each token in a given data set, and just exponentiate it. And then perplexity will be a positive number where lower is better. And this basically tells us just how well is our model modeling a given distribution, how well is it fitting a given data set. And so there are a couple of pros and cons of perplexity. A pro is just that it is very directly correlated to the language modeling task that we train these models for. And so it's good for evaluating these sort of base language models just trained to predict the next token. And it also sort of scales smoothly with the loss. So it can be useful, especially when we're sort of pre-training models, to run perplexity on an additional validation data set. Another benefit is that it's very cheap to run. We could just say, basically, take the text of English Wikipedia, tokenize it, and feed it through our model to compute the perplexity. We wouldn't have to have any sort of ground truth labels or formulate this into any questions. So this is sort of a very low-cost way of measuring closeness to a data distribution. But by the same token, if we tried to evaluate the perplexity of a model trained for the chat format on like Wikipedia, this would just not match the distribution our model was trained for anymore, and so it wouldn't be as useful unless we were measuring perplexity on actual chat completions. And it's also not really super well tethered to how well the model can actually generate free-form text when we try and sample from it. So that's perplexity. And the other somewhat related method that we have to sort of interact and gather information from a language model based on some input and output pair is something called conditional log likelihood. So basically, if we have some input string, this might, for example, be the sort of question or prompt in a given benchmark example, like the cow jumped over here in this instance, and we have some target string that we know should come next, like in this case, the moon. We want to figure out, basically, conditioned on the model seeing the cow jumped over as input, what is the likelihood that the model produces this correct continuation, the moon, as output? So we want to find the log probability of a potentially multiple token target string given an input. And because of t-shift forcing, this is actually cheap to do. If we want to compute the log probability of some string y given x in only one input passed through a language model, we can feed in the concatenation of x plus y to our language model. And in order to calculate the log probability, we just want to figure out what the probability of the model assigns to sort of y sub I, the ith token in y, condition on its input x, and the previous tokens in y. And we want to do this for every token in our target string. And so summing up these per token log likelihoods will give us the overall likelihood of this multi-token continuation. And because of the fact that models output logits at every sequence position when we feed in an input, when we feed in x plus y, we have this logits L. And basically, if we just look at the model's prediction for the token that comes after n plus I tokens, or the model's prediction for n plus I minus 1 tokens, and then we look into the logits and check how likely the model thinks that this true next token value should be spit out. We can just basically calculate these log probabilities per token and just sum them up by indexing appropriately into our logits. And so this is just one pass through our language model to get how likely it thinks some like gold standard true string is. Yeah. And so the most common way that these log likelihoods will be applied is in a multiple choice formulation. So again, using this sort of toy example as a stand-in for maybe a multiple choice test question, we have some input, which is sort of our prompt or our document, along with maybe whatever context we desire. And then we have a few different answer strings, just like 4 in this case, which is sort of a closed set that we have access to already. And so we know that one of these is correct, and the other ones are sort of alternatives that maybe a model might spit out if it was misinformed about the answer to this question or the next way to complete this sentence. And so, converting this into an actual multiple choice question, we might present a question as like the question to the model, then give it the answer choices in context, does A, B, C, and D, and then prompt it with answer : and then check what the likelihood of producing the token A is, the token B, the token C, and the token D. And so what we'll do is we'll run our basically algorithm just by feeding in the concatenation of this answer string and the original context, and figure out how likely it thinks this answer is, how likely this answer is, this one, and so on. And then whichever answer the model would be most likely to produce, even if it's not sort of the argmax string that the model would produce, can become the answer. And in this case, the model gets it wrong because it judges A to be the answer, but D is the correct one. But this is how we would formulate multiple choice in a way that's efficient to pass through a model. And so this has several advantages and is a pretty common format for evaluating language models. It's nice because out of these 4 different choices, we know that our language model is only ever going to pick one of these 4 that we've allowed it to, because we're sort of only comparing the likelihoods of these different closed set of strings. And so multiple choice is also comparatively efficient to evaluate because you only need to pass in, say, if it's a yes-no question, only 2 different strings into the language model, or only 4 different strings into the language model. And it is still closer to the sort of training distribution of predicting the next token. So it can be, if formulated and prompted correctly, it can be pretty good for base language models as a result in sort of showing signal. But a downside is that most real-world tasks we want to use these models for are not closed domain. We won't have sort of a couple multiple choice answers that include the correct one per se. And yeah, again, like we're not asking models multiple choice questions. We're asking them to be chatbots or other sorts of things. And so the final way, of course, to evaluate a language model is then just generating text from its distribution, where we take the logits that we get out for the final position, which is basically containing information about what it thinks the next token is. We can use the softmax to turn this into a probability distribution, and then sample from this using various strategies to get a next token from our model. And this is how many models are used, especially when they're sort of chatbots. But there are some caveats here because we're not artificially restricting the output space to these sort of 4 multiple choice answers that we can know which one is correct and which one is incorrect. We have to somehow be able to sort of solve this key problem of scoring a free-form natural language. And so one way to do this for things like math word problem answering, where we have the model produce some solution or rationale and then produce its answer, is we could say, okay, in our few shot examples, we'll give our model basically rationales in this format where it says the answer is some number. And then we could just use sort of a rule-based or regex approach to find what is X, where the model outputs the answer is X, and just return this as our answer, and then grade basically is the number the model spit out, 9, the correct one or not. And so this requires basically designing heuristics based on your problem setting, and sort of hand writing these so that they capture all of the output formats a model might create, which you're going to eventually miss some of these output formats. And then another thing people do is they can use an LLM to sort of extract the model's answer from this preform text. We won't talk about that too much in this tutorial, but this can also cause problems and is, again, not going to give you the answer you expect for every single output. So basically here, there are some pros, obviously, which include that this is sort of a realistic setting to evaluate our models in, and that it allows for us to use things like chain of thought, which many models are often now trained with in instruction tuning as sort of their expected output format. But there are downsides, which basically include the fact that we have to solve this issue of scoring freeform output somehow. And if we do some sort of fragile parsing setup, then we're going to skew our scores somehow and sort of favor models that use our expected output format, and so on. And it is much more expensive to run this as well because you have to repeatedly generate and produce next tokens from the model as compared to multiple choice. And there's also other problems, like you have to sort of decide what decoding hyperparameters or algorithms to select, which might be pros or cons. And so all of these methods, at a high level, these are all used for language model evaluation. But under the hood, there are actually a bunch of hyperparameters that can be varied and that strongly affect performance. But at the same time, these sorts of hyperparameters are not often specified and described in every paper that runs evaluations on their models, zero shot. So one major complication here is that models don't operate just purely on strings. They operate on tokens. So basically, we have to take our tokenizer and feed text through it to convert it into a number of tokens. And this can be very brittle and sort of hurt our comparisons across models that use different tokenizers. So as an example, for log likelihood-based multiple choice, when we have different multiple choice options, which are different numbers of tokens in length, the model is going to prefer shorter completions by default, just because the likelihood of producing a multi-token completion is the sum of these negative values, which are log probabilities. And so in order to not make our models just artificially favor the shorter answer choices, we need to do things like either divide that log likelihood sum by the number of bytes or the number of tokens per answer choice, or do things like sort of normalize against a baseline of how likely our model is to produce this given string of tokens based on the empty string. And And so various sort of forms of normalization are used by people, but this is often not shared. And the quote unquote best normalization for performance varies by data set as well. And for perplexity as well, because different tokenizers will sort of divide up the text into different numbers of tokens and different division points, we also there still have sort of a different denominator, and so can't easily compare perplexity numbers across tokenizers. And so there are some fixes for this, like bits per byte, which basically ends up checking sort of what the average log likelihood per byte of the input is instead of per token. And even freeform generation approaches sometimes have issues with tokenization. So these two prompts are an example from the human eval coding data set, sort of in a prompted format. They look more or less the same, but if you use this prompt too, your performance for some models will be 5 or 10% worse than using this prompt. And the only difference here is these sort of trailing new lines and tab character, where because these tokenizers are very brittle and they might have a character like new line, tab, or tab return as sort of a Python character, adding this tab at the ends will force the model to produce just the raw return word, and this might be a different token, and throw the model off and not really make it as effective at generating code. And so these sorts of details would include basically how much white space do you stick at the end of your prompt. They seem like they might not matter, but they actually hugely impact the scores you get out. Perplexity is also affected when you're trying to evaluate very long documents by confounders like what the context length of your large model is. Because basically the first token in a document has no other tokens to condition on and is basically starting from the empty string, we just don't know what this token should be, what our prediction here should be. And so basically the first tokens in a document will always be harder to predict and have a higher probability or more error that the model has and less certainty. And so basically the way that you divvy up longer documents than your model's context can change the scores that you get out significantly. And again, this is something that is sort of folk knowledge that's underdocumented, but has a major impact and sort of only lives in the implementation details of evaluation code bases. So basically, in conclusion, these fundamentals are sort of all the same and share commonalities, but many papers reporting evaluations on language models sort of underspecify their setups and which of these hyperparameters they choose at a fundamental level. And this is problematic, especially because out of these implementation details, there's not necessarily one correct choice out of all of these to use. You could use and argue for any sort of normalization for multiple choice, for instance. And so knowing what people used, knowing what the best choice to use, and how to implement all these things requires sort of tacit knowledge and experience in the field of language model evaluation, which is what we're trying to sort of solve with this tutorial, and sort of bringing some of this stuff that's not actually talked about in publications to the forefront. And so now I'm going to talk a little bit about some of the other complications that language models uniquely introduce in evaluation. There are many, and there's also problems with evaluation that needs to be accounted for even outside of language models, but we'll try and focus on the language model point of view here. So first of all, a major consideration that we're going to try to reach is reproducibility. Basically, can we fully document and potentially share our evaluation code bases so that any sort of number reported in a paper on a given language model can actually be reproduced by someone else after the fact? So this example is basically the evaluation headline numbers reported by the Claude 3 family of models. There's some sort of details on implementation reported here, like this task is 3-shot chain of thought across the board. Let's see. This task, some people evaluate 5-shot, some people evaluate 0-shot chain of thought, some people evaluate 5-shot chain of thought. And so these sorts of footnote details are very important to what sorts of scores you're going to get out. But again, you sort of need the entire story to reproduce numbers perfectly, and be sure that these comparisons are fair. And another core reason that reproducibility is going to be so important and sort of attention to detail is so important is because language models in particular exhibit non-robustness, but in ways that are counterintuitive to humans. So sort of the failure modes of language models will not necessarily be the same things that we might find a human task performance to be non-robust to. So one example of this is prompt sensitivity and formatting. Sort of the choice of prompt used for evaluations can be make or break in evaluation scores, and evaluating a model with, say, sort of the wrong white spacing, a different format, can make a huge variation in evaluation score. And so properly reporting the prompts used and why they were used, and if any prompt engineering was done, is vitally important. And again, like here, a human seeing this and just not seeing a space in between these two words, we would expect the person to do just as well when there is this white space there and not really have this be something that affects their performance on the task. And yet for models, it can tank their performance, either because of distribution mismatch with their training or just because sort of variation across prompts. And so another core problem is that even across, say, sort of reasonable formulations of multiple choice, like the difference between this sort of MMLU style formulation where we give the model its answer choices in context and have it produce the answer letter versus a more language modeling format where we ask the model the question, don't give it the list of possible choices to choose from and have it produce the answer string. You're sort of more of a just like next token completion format. These can hugely impact scores. So for example, this is like a 25-point difference out of 100. But the problem is that across model families, so some models are better on this different style, MMLU style prompt, some are better on this closed style prompt. And so there's this problem where there's sort of, again, there's no right choice that we could make and that we could say sort of all of our issues are solved. And we don't really have to worry about unfairness due to prompts. If we choose any sort of prompt format arbitrarily, we're going to favor the models that were either trained to expect this format or are just performing better on it for whatever reason, maybe due to their data set and so on. And again, like, so this, because different models prefer different prompt templates, if we chose this prompt template, we would think that this model is the best. And here, like, it does happen to be the best on the second choice, but for the rest, their ranking hugely shifts across sort of different possible alternative prompts that could have been decided. And so this is a problem if we're trying to compare models, because if we just pick one prompt, then our rankings are different if we just pick something arbitrarily equally quote unquote correct, but just not the same choice. And so another sort of further complication down this rabbit hole is that the few shot examples we present to a language model can impact performance significantly. In the case of this plot, this is showing basically variance across different choices of few shot example for various GPT-3 series models. At least in this case, the GPT-3 175V model performs well across all few shot example choices, but that's probably just because it's very good at this task. But for the other models, the few shot examples can either make them do very well on the task or worse than random. And as well as the choice of few shot examples, making sure they're, say, class balanced and so on, the ordering in which we present the few shot examples can also impact performance. And this is another detail, which even if people do report the prompts that they used and the number of shots they used, they might not report their selection strategy for few shot examples. Another complication is, again, like one sort of possible solution to all of this could just be, okay, well, let's just sort of take every different model family and prompt engineer manually until we get a prompt where our model performs well. But this can heavily overestimate the performance that we end up seeing and sort of mislead as to how good these models are. And so in conclusion, basically, there's sort of a massive butterfly effect here with evaluation results and scores that's created by these minor implementation details of how evaluations work under the hood. And so we really have to sort of worry about the basics of how we implement evaluations. And again, another thing here is that a difficult thing to answer is basically, what should we be doing if we want to do a fair comparison against a baseline or apples to apples comparison of two different model families? There's so many options. We could pick the best prompt out of, say, a set of 10. We could pick the worst performing prompt. We could just evaluate all models in exactly the same prompt format and so on. Many different choices to consider and no real clear answer for what makes a fair comparison, at least universally. Because fairness will often sort of be a context-dependent question based on what research question we want to answer. If we're trying to sort of deploy models on device, then we want to minimize the number of parameters and the VRAM required. But if we're trying to train the most efficient model, we might care about minimizing training flops and compare models across the same amounts of training flops used. So this plot, for example, is from the paper Cerebrus GPT, where basically the green is the Pythia language models, which is a set of models all trained on 300 billion tokens, which for very small sizes is massively past the sort of optimal allocation. And for the Cerebris's family of models, they train according to the sort of chinchilla optimal ratio, which what this tells you is that if you only look at the training cost, the number of flops used to train these Cerebris models for a given compute budget, they will massively overperform these sort of improperly allocated, smaller but more data Pythia models. But if we're trying to hold comparisons equal, assuming that we're going to use these models a lot downstream, and that we're going to say like run at least 2 trillions of tokens worth of inference on these models once we've created them, then all of a sudden the sort of calculus for which is more efficient very much changes. Because these models were previously overtrained, now that we're using them a lot and they cost less to infer, all of a sudden they're more efficient for the same sort of loss. And so basically, like the comparison we're going to have to make is going to have to depend on our purposes. Yeah. And then another complication here is we've been previously talking about just sort of base language models, but the frontier models of today are increasingly systems instead of models. So they're trained with various sort of extra features like retrieval augmented generation, memory, all sorts of things that sort of confound easy one-to-one comparisons across models. So these sort of also further change the calculus of what a fair comparison is. Another core problem with language model evaluation that has to be overcome is the issue of dataset contamination. So like previous evaluation datasets to some level assume that we're trying to test models' generalization, zero shot or few shot to some new task that they've not seen before. And we're assuming that this is a sort of novel dataset that we can like make claims about zero shot on. But the problem with language models and their sort of massive scale of datasets, where they're trained on basically all the internet we can get our hands on, modulo some filtering, what data is worth it. Basically, we have this problem where almost everything that you can sort of imagine seeing and that you could sort of source a data set from, because many data sets are created based on, if not via directly taking internet content, sort of by construction, these data sets are already leaked into the pre-training data sets. And so these assumptions of novelty and generalization might not hold, sort of challenging the validity of these evaluations. And this contamination is very difficult to prove because even sort of non-verbatim contamination might overestimate our model performance. For example, if we train our model on not the MMLU dataset, something that would be caught if we tried to look for sort of exact matches to the dataset questions in our data, but instead train on just a like LM paraphrased version, our performance increases significantly. Even though we might sort of using n-gram methods, we might think that this is a clean dataset to train on, which is a challenge to be thought about when building synthetic data sets. And so, like, since sort of many things and there's sort of many degrees of contamination, we have to sort of think about what counts as contamination and what's just sort of training on the internet's benefits. And we also have to think about, as a field, how we can design contamination-proof evaluations. So one thing that many people are doing is trying to collect sort of novel data that refreshes frequently so that we can evaluate models that are trained beforehand or trained on data sets that were collected before the creation of these data sets. But again, as soon as these test sets are released in public, they sort of become to some level contaminated and are able to be optimized on, making it hard to like hold out a truly contamination-proof evaluation set. Another complication here is that there's not really a super clean division between base language models and instruction tuned language models nowadays. So many works, including Olmo 1.77b, which does a great job of documenting sort of their progress by upgrading the data set to make MMLU score much better, basically found that including, among other things, some instruction formatted data in the pre-training data set massively improves downstream task performance, which seems logical. And in this case, for the Flan dataset, which is an instruction dataset that they include in their pre-training, it does not include the MMLU dataset, although it has many other tasks that are components. And so there's this question of sort of whether this is cheating or whether we just care about having models that are good at the sorts of downstream tasks we want to use them on. And I don't think that this is cheating, but it does sort of challenge, again, some of these assumptions we make about models sort of zero-shot generalizing to follow instructions. And so basically the conclusion of this is that there are sort of unique challenges in benchmarking that language models pose. The details really, really matter for implementing evaluations, and so it's difficult, but very necessary to do reproducible evaluation. The right sort of evaluation choice is not going to be universal and has to be thought about in context. And there's sort of novel validity challenges that we need to reckon with that are introduced by the massive scale of these models. Like language models sort of at times work well because everything we test them on is somewhat in distribution, but it remains to be seen how we can sort of reliably design evals that effectively test generalization to unseen data instead of just measuring sort of memorization of the internet. Yeah, so with that, I'll hand it back to Lintong, who's going to talk about some of the other considerations that are less LM specific in sort of benchmarking and evaluation.
So complications regarding general benchmarking. Why, in this section, I'd like to talk about why it might be difficult in general and what are the challenges in constructing useful data sets, useful tasks that are used to evaluate these language models. I think it's good to start by reflecting on where benchmarks do come from. And it seems that the trend seems to be either that benchmarks arise from things or capabilities that we wish or that we want models to be able to do. For example, how Squad emerged to evaluate whether or not a model, how capable a model is in doing reading comprehension, or the MMLU benchmark arose from to observe whether or not models are capable of multitasking, answering across multiple different subjects and different levels of grade education. On the other hand, it is interesting also to see whether or not language models build benchmarks for language models due to the fact that they produce certain unwanted behavior, such as toxicity, or that the fact that they hallucinate, that also motivates people to create benchmarks that are able to measure this. And so typically when a benchmarks are made and its inception phase, it can either fizzle out and we might never know that it existed, or it could start to gain traction as we see for benchmarks such as MMLU, Superglue, and so on. And then it becomes active as more people are interested in evaluating their language models on these tasks. But then there is a stage where it reaches a certain maturity where it doesn't seem that a lot of progress is being made, or if there are, the delta of that progress becomes less and less meaningful because of the improvements that is able to achieve, or that it saturates. And so this is typically a sign that it needs to be renewed. For example, how Glue is then renewed into Superglue and Squad is renewed into like the second version. However, that also does not last forever, and it becomes an incentive or a motivation to create new benchmarks that are based on what seems to be the case where models have learned or have solved certain cases. It used to be the case that benchmarks typically have a longer life, and this seems to saturate after about 10 years or so. However, it seems that current benchmarks saturate very fast. And the issue with this saturation is that it becomes less and less useful the smaller improvements that we see. But other than that, it seems that benchmarks do influence progress. But one way that we could say it benefits by knowing what works and what doesn't. But on the other side of the coin is that there are selection biases that can hamper progress in developing new approaches. For example, how task selection here, it's certain architectures or certain approaches are favored by seem to produce better results on certain tasks. But then there's a more harmful other selection bias, which comes from the community itself. As benchmarks become more mature, or they become actively used, there is a certain expectation maybe from reviewers to say, why is this model not evaluated on this specific benchmark, and that could also lead to other practitioners or researchers maybe self-selecting themselves by not wanting to publish their findings simply due to the fact that it doesn't perform necessarily well on certain benchmarks that people expect models to be evaluated on. This leads to the issue of overfitting, and I think it's very apt to cite Goodhart's law that when a metric does become a target, it ceases to become a good metric at all. And I think this we can see that it's a very real case in the case of GSM 8K. This work is GSM creates a data set that they name GSM 1K, which is supposed to be IID from GSM 8K. And what we expect from two sets that are IED is that they should have the zero changes in performance. But in reality, the majority of the models that are tested with GSM 1K do perform worse than GSM 8K. So even though it may not be intentional, there seems to be an overfitting on this typical data set. And so that leads to what exactly is a valid, what makes a valid evaluation, a valid benchmark. Benchmarks are frequently proxies of real performances. However, certain benchmarks, as Safra et al. Pointed out, may not, in fact, be a good proxy. And so then the question becomes more of two factors about validity, being the measurement validity that talks about whether or not a benchmark does, in fact, measure true capability, and measurement reliability, that if we are able to measure a certain outcome, is this necessarily something that is consistent or reliable when we have these scores? A good example of tasks that may not be valid is something that McCoy et al. Pointed out, where benchmarks can be faulty or be solved by models by relying on something other than what we intended to be measured. For example, how in certain natural language inference tasks, McCoy et al. Had found that it can be the case where models are able to use spurious heuristics to kind of solve these tasks. An example being either the lexical overlap, or if, say, the premise the premise actually has all the words in the hypothesis, or if it's either a subsequent or a constituent. Like if it's either in one sentence is in like the previous sentence, then a model is able to like capture that and just learn to perform very well, even though that's not really what we want the model to do. Another case could be about the issue of generalization. One benchmark could be that we evaluate on arithmetic, and we typically use base 10, but then, and it performs quite well. But then if we change that to base 9, which is a valid way to do arithmetic, models may not perform well. So this is kind of a blind side in defining maybe the scope of what a benchmark should do. Like if one claims that a model is able to do arithmetic, it might be a blind spot by not saying that what are the specifics of these arithmetics, when in fact it can be expanded further. So it's also, I think Liao and Xiao introduced an interesting way to look at benchmarking in terms of two-dimensional axis, one being a context realism, or how good or how close it is a benchmark to like the contextual use cases of a performance that we're trying to measure, or the human requirement realism axis that measures how close a model is able to perform a certain task that has utility to a person. The lowest level of this would be normative benchmarking, which is the typical benchmark that we see today, MMLU, ARC, and so on, that has a automated set, an automated evaluation, a ground truth, and so on. And the idea here is that as further up we go on the realism axis, the closer it is to an actual performance that we wish the model to have, but at the cost of being either expensive or time-consuming or both. There are alternatives, though, to being to measure these models, and one way to go about it is to measure the output quality based on a specific utility, or a utility towards a specific downstream application. A good example would be how to evaluate machine translation models, for example, based on how many manual corrections a person would have to make. Or to evaluate translations or summaries by answering reading comprehension answers reading comprehension questions based on those artifacts, which could be either done by a separate model or a human as well. So, but what happens when scores do become less meaningful? There seems to be a saturation, but some of these models saturate at around 80%. I mean, even having human involved in the evaluation in the baseline, there seems to be a saturation that doesn't even reach 100%. And as it turns out, this could be due to like error within the data set themselves, as Gemma et al. Discovered that there are observed errors in the MMLE sample, and this becomes even more important as we see the saturations, because it could be the case that models actually answer samples correctly, but because of these benchmarks having these errors, they are still considered wrong. Gemma et al. Presents multiple categories of error that they found, but more interestingly is that they developed a heuristic which seems to be applicable to many other cases, any other benchmark, where they first start by assessing the quality of the question and then go towards verifying the ground truth. Also, but when it comes to the metrics of the benchmarks, it might also, the selection of metrics could also change the conclusion that we have. As Schaffer et al. Pointed out, that when using nonlinear or discontinuous scores or metrics, we can observe emergent capabilities where suddenly as the model size grows, it seems that the accuracy, the score itself, tends to also go up suddenly or rapidly. But if we instead use linear or continuous scores, for example, so Breyer score or token edit distance, then the performance seems to be more predictable. It seems to be more linear. And so the choice of these metrics can also influence the conclusion that we take. However, automatic solutions, automatic metrics themselves may not lead to the best results, as multiple works have pointed out that Blue may have impeded progress in MT due to it favoring certain models over the other. Basically, models that prefer to produce n-grams that are closer to the ground truth instead of like focusing on the semantic meanings. Rogue favors systems that produce longer summaries instead of summaries that focuses on whether or not these are effective summaries or not. And so it might be tempting to then fall back on human evaluations. But then again, human evaluations themselves are very diverse. In many works that use human evaluations, there are many criterions that can mean a wide range of things. From fluency to coherence, these are things that may need to be explained both to readers as well as to the human judges themselves. The quality can also vary when using human evaluations. The quality that being judged can be either correctness or goodness. The forms could be either looking into the grammatical aspect, or is it looking at the meaning, focusing on the meaning and not so much as caring about whether or not the grammatical is exactly correct. But then it also can lead towards evaluating on things that are subjective to a person, like their preferences, or it could be objective, like the co-occurrence of certain texts or certain words. However, human evaluation isn't really a gold standard, as it does lead to divergence due to background knowledge, preconceptions of the language, if people have different understanding of what an instruction could mean, as well as the general educational level of a population that is being asked to evaluate. There might be differences due to differences in population. But if in fact the human evaluations could still be adequate in certain cases, it is important to, first of all, define the criteria and define this not only for readers, but also for the users, to make sure that everyone, or the human judges, do have a common understanding of what is being evaluated on. And also to use an adequate sample size as to be able to provide a meaningful score that is statistically significant. text samples that are being evaluated should also be evaluated based by multiple people to kind of understand whether or not there are disagreements within the population, and also use certain quantitative scores like Likert scales that can help, or that has like a theoretical or is heavily used in other fields such as psychology. Lastly, for human evaluations is that it's very important to kind of at least discuss how these measurements were made, the general population, or any specifications that could help other people reproduce or understand the work that's being done when using human evaluation. But other than automatic and human evaluation, new metrics that have arisen have been increasingly neural network based. For example, BERT score that reuses BERT to output a score of similarity, as well as a new kind of a recent paradigm that talks about how language models can be used to judge outputs of other language models. Now, there are still many issues, for example, how language models could favor the outputs of other language models or specific language models when compared to humans, or that these language models themselves may have certain biases that we don't yet know or not able to measure at the time of using these as scorers. Lastly, when we talk about metrics, while I did talk about how blue may not correlate to human judgment, or that might impede machine translation progress, as mentioned by a few works, it may not necessarily be desirable. For blue to not correlate to human judgment might not entirely be a bad thing, because of course the signal that we get from blue, for example, is a measure of how well the model output overlaps the n-grams to the ground truth. So maybe in certain cases when we do want model output to be faithful to a certain ground truth, it is important to use these. But at the end of the day, instead of relying on a single score or a single measure, multidimensional measurement could be a much more substantive way of evaluating how models perform. When we already do have a score that we have, direct comparison is not always straightforward, as shown here, that even for multiple models across multiple works evaluated on the same task or benchmark, ARC challenge or open book QA, these scores can't really be directly compared to, as there are many variations. For example, how the number of shots in one paper could be 25 instead of 0. The few shots could be either curated, they maybe are not, and the formalization, whether they're closed format or multiple choice format, also can vary the scores. So it really comes down to what we really do want to measure, because certain models tend to favor certain prompts, certain outputs, certain formulations rather than others. So in the case of, let's say, we want to measure models that are trained in below 500 billion tokens, it might be wise to use a certain formulation here, closed formulation, rather than multiple choice formulations. In the case of prompts, this is a callback to the earlier slide, where the prompts themselves can, in fact, influence the output. It's important to keep in mind when we do want to evaluate on certain tasks, what prompts do we want to use. And in fact, it might be a good idea to use a set of prompts and consider that as part of the benchmarks themselves. However, of course, the downside becomes if you have a set of 10 prompts and you have 1,000 samples, then automatically the benchmark explodes to 10,000. And so it might be appealing to make these benchmarks smaller by targeted sampling. Here, by Polo, they propose an IRT++. It kind of shrinks the benchmarks to only 100 samples that are perceived as the most influential in determining like the overall score, which tends to agree with like the true performances. However, shrinking may not offer the full picture, since even though that there is a agreement in the mean performance, the standard deviation may not naturally agree. And so when it comes to modifying these benchmarks, it might be important to also do additional analysis, especially on the standard deviation, whether or not and prefer a standard deviation that is much thinner here, as that would result to like a stronger statistical significance in the benchmark. So probably shrinking could work as long as there is a sound justification and procedures that allow it to naturally or to at best represent the original data set. And so, to sum up about benchmarks, it's an interesting to kind of cite from Bowman et al. That, benchmarks is they should imply robust in-domain performances. They should have examples that are accurately and ambiguously annotated. So if one were to use certain benchmarks, it would be a good idea to, again, review these benchmarks and see if there are certain errors in them, especially if they are starting to saturate. Statistical power, again, talking about the standard deviations of these benchmarks, is important to make sure that when you do have a number, comparing a model A that does 99% and another model that does 99.9%, you could say with certain confidence that the one that does 99.9% is in fact better and not exactly the same. And so, to conclude this section, benchmark is indeed difficult. But however, because benchmarks dictate what we measure, what we end up building, we should ensure that the validity of these evaluations, in order to make these findings actually useful, and that careful data set construction, modification, and selection of the metric is a crucial thing to always consider and report. So how do we address language model complications as well as benchmarking complications? What can we do today? For starters, there doesn't seem to be a standard, and maybe there shouldn't be a standard at all. What people do share, there doesn't seem to be a set of checklists that people have to produce. But what we do know is it is beneficial, or at least for either like the writer, the authors, or the readers to share, be that evaluation code, the methodology details, or the model responses themselves. However, we might not suggest to overshare. If one were to build a certain benchmarks, it might be wise to have a private test set just to ensure that the public test set is not being overfitted, right? And that kind of becomes a good signal of whether there should be some renewal or some action would need to take to kind of update those benchmarks. And so sharing code seems to be the best option. A lot of people would say, if you ask them, would say they would probably be in favor. However, it's still not the case that some notable works, still don't release certain evaluation code, which makes evaluation or reproduction more difficult. However, sharing code does serve as a ground truth reference point for the methodology. So if anyone were to reproduce, they could always refer back to the evaluation code of the original source to make sure that it's working. But say that a model is very big, or if an API-based model changes over time, instead of only sharing code, it might be wise to also share the model outputs so that future evaluation metrics, future evaluations in general could be redone without having to spend high cost. Or in the case of APIs, basically that means you would never be able to reproduce whatever output that was generated at that time, since it was updated. Another good thing to do would be to avoid copying results altogether. So if, say, we would have a certain approach and we want to evaluate it on a certain baseline from other papers, then it would be wise to either run that evaluation code on the settings that we have or to reproduce it on our own implementation of evaluations. As drawing baselines, as shown as in previous slides, are likely to mislead due to like the fact that there are simply a lot of variations that we might not account for if we haven't checked carefully. It also helps to run experiments multiple times. A lot of papers seem to only put one number, which then doesn't really offer statistical insights, whether or not it's significant or how much it varies. As benchmarks become harder, it seems that the trend is it becomes smaller and smaller, and so it's much more important to have statistical significance testing, especially when the tasks are small. So to operationalize these best practices, re-implementing evaluations using code seems to be the best case. However, it may be also provide a challenge, time consuming. That's why using existing evaluation libraries as infrastructure might be the best way to kind of lower the overhead of adopting best practices. Fortunately, there have been a lot of tools to do just this. Not only the language model evaluation harness that Haley and I have been maintaining, but also Helm, OpenCompass, and also Inspect AI, which is relatively new. These libraries have their own different philosophies and intentions, but the general gist is that these software help users do evaluations and reduces the overhead of having to re-implement everything from zero. And of course, there must be multiple other existing tools that we've never heard of. So future directions, like to give this to Haley.
Yeah, thanks so much, Lintong. So to close out, I'm just going to talk about a sort of non-exhaustive list of some of the sort of future directions for creating better evaluations or sort of new evaluations for language models. What is out there, what's not out there yet, and so on. So, first off, like one thing that's very clear as sort of like a new trend is that most state-of-the-art language models are not just only trained on text. They're often even sometimes natively trained on both like text, images, audio, and many different modalities. And so creating evaluation tasks, there are plenty now already, but sort of creating and defining further best practices here and figuring out both sort of what tasks we want to be in practice using multimodal language models for, and how do we want to evaluate sort of multimodal understanding well as understanding multimodal generation. So this is sort of a whole other consideration compared to just text output, even if it's multimodal input. And so like expertise really needs to be transferred from other communities like computer vision into like language models and language model evaluation for these new cases. Another thing is there's plenty of room for sort of more creative or more sort of specialized evaluations. Like for example, reward bench is a data set that's specifically made to evaluate the quality of sort of reward models trained on human preferences, which would give a score to sort of given model outputs. And so these sort of specialized data sets are also something that can be explored for different use cases. Many models are also trained to do something called tool use, basically incorporating external information, like say like calling out to a calculator or running a web search and putting the results in context. And so like while best practices for training this way are evolving, evaluating models' ability to call tools or multiple different functions at once is something that needs more work done in evaluation to further this field. Then another area that's expanding is basically using models in sort of loops or sort of agent use cases where they're integrated into external systems and environments further than just sort of a static question answering format. And so basically evaluations should keep pace with these applications and reflect basically how good models are at performing these sorts of tasks. One example of this that's pretty notable is the recent data set SWE-bench, which basically evaluates models' ability in the wild to sort of operate on an entire repository of code and close real GitHub issues. So these sorts of evaluations are both harder to create and harder to evaluate, but are also closer to downstream usage and sort of economically valuable tasks. And so for this reason are sort of much more compelling as compared to sort of more choice examples like multiple choice. as other things like evaluations that are perhaps harder to sort of create as static artifacts, like red teaming, where often human or maybe model annotators are sort of just interacting in a free-form way with the model and trying to elicit harms and avoid guardrails created for safety. And this is like an extremely important and useful topic that requires like lots of expertise, hiring and paying human annotators. But it's something that could totally be improved, especially in the area of sort of automating this and bringing down costs for this sort of thing. So all sorts of sort of more dynamic evaluation processes than just static evaluations. In general, the topic of sort of creating evaluations that are more resistant to evaluation gaming and contamination, especially as we sort of heavily hill climb on our existing public benchmarks, is a very important open question that still is not sort of fully solved. And creating benchmarks that we can really use to test out of distribution generalization, especially in the long term. And so, for example, holding out additional private test sets that aren't just held, that where not just the labels are held private, but also just like keeping the existence or the entire data set private until it can be used sort of post hoc to identify overfitting to the public test set, can be useful. But as soon as that further private test set is disclosed and released, this sort of loses its usefulness. So it's still sort of an open problem. And then lastly, I guess just in general, the area of dynamic evaluation data sets instead of sort of static groups of questions is something very interesting to consider. There's been previous work on this in the past in the field, especially with sort of adversarial benchmarks like DynaBench. But there's other future work that's been more recent that's looked at basically if we have sort of a very specific capability we want to test a model for, can we create an evaluation on the fly, maybe a very small test set to sort of diagnostically check our models for this property, which is especially important because, as mentioned before, as language models sort of solve more and more tasks that are more and more difficult, it's more costly and harder to collect the data required for these complex capabilities. And so test sets are getting smaller and smaller out of necessity as a result. And so this sort of automatic generation of diagnostics, especially for sort of specific capabilities, is very interesting. As another final area of interest is that scaling laws have been fundamental for motivating and allowing efficient scaling of large language models with greater and greater amounts of compute. And they let us sort of de-risk these scaling experiments and extrapolate out estimates for what our return on investment as we increase compute will be, but only for pre-training loss. And so while there's some preliminary work on this, really figuring out how to predict how well our models will perform and how well their performance on actual downstream tasks of interest will scale with compute is a very important question to answer, especially as we spend more and more on these models. So just like a couple takeaways from the overall talk are basically currently there's a lack of some clear reporting standards and best practices defined in the language model evaluation fields. And it would be great to have some of these defined so that we can at minimum sort of improve the standard of reporting in the fields. And that reproducibility is crucial for drawing sort of one-to-one comparisons between models, since the models are sort of counterintuitively non-robust in many ways. And there's sort of many, many exciting areas for future research, including just like evaluating models on more complex capabilities, more sort of dynamic and complex evaluation processes, and so on. And so I hope that this will sort of give people an idea of where we're at and where we can get better and how the field can improve. Yeah, thank you.
Thank you very much. What is your opinion on the LMSys benchmark chatbot arena? If you know what I'm talking about.
This is good story. Yeah, I can. Yeah, so I think like benchmarks like LMSys definitely serve a very real like purpose and fill a great niche in the community. I think like very distinct from sort of static benchmarks. Like I think this sort of preference evaluation is very useful for these chatbots downstream, but I think it's a bit tricky to evaluate sort of more complex qualities like factuality using human annotators, especially ones that are sort of non-expert. Because one thing that Lintong was talking about is sort of human evaluation is not always really the gold standard because humans are vulnerable to the same biases that like language models as a judge are. So like a chatbot that just outputs like a more assertive sounding answer or a longer output will just be preferred by people, even if it's not more factual. So it's sort of difficult to resist gaming even in this case.
Thank you for the talk. I was curious, do you think it's really fair, especially on the smaller labs, to say that, as as you suggested, we need more samples, we need more reproducibility, more runs to really evaluate models. Do you think it's really possible for smaller labs to produce valid evaluations that would accurately convey the capabilities of their models?
Okay, so basically it seems like benchmarks are getting more compute intensive, how to, still produce better evaluations. So I think we have seen like even small evaluation data sets, although it's costly to pay sort of expert human annotators to create this data, I think like smaller evaluation data sets can still be super valuable for the field. One example is GPQA is a recent data set that's been sort of very high profile. It's only a few hundred samples, which is difficult for like, statistical significance reasons, but is still useful because you're sort of needing to still create harder and harder tasks at any cost. I guess like, I'm not sure if that's a satisfactory answer to the question. I think it like one area of active research is like how to do evaluation more cheaply, which was discussed by Lintang. So I think this is an area that is useful, at least to like better performance estimates with sort of a set amount of compute or of data. Yeah.
Sure. Thanks for the tutorial again. So two things. So what are like the effects on like market force? What are the market effect forces on the cycle in terms of evaluations? Because right now, if a big enough player puts out says, here's a new evaluation that we're using, even if they didn't create it, it affects the rest of everybody trying to then rush to then include that evaluation. Second, how then also does that maybe keep away that there might be diverse evaluations that are available? It's just that they, again, maybe connected to the previous question, are coming from smaller places that don't get as much attention, but they actually do provide information that is not out there. So I don't know how maybe we balance those two.
Yeah. Do you want to take that?
I have difficulty hearing. It's okay if you answer.
Oh, okay. Yeah. So I guess the question is about how to sort of account for these social factors of people sort of adopting all of the same evaluations, right? And specific evaluations being centralized as the ones to test on. I think this is a bit difficult to counter and accept just by being conscious of it in your own research and sort of trying to improve these norms here and select more diverse evaluation data sets. I think there is extreme pressure for people releasing models to evaluate on all the same benchmarks that their competitors do, because just you have to draw comparisons somehow. I think that just basically in general, I think people should make sure to vet their data sets before just blindly adopting the ones that everyone else seems to be using. And I guess so also in relevant to the social factors is, so we maintain the LM evaluation harness, which is a tool to make it easier for people to prototype new evaluations and just sort of run standardized pre-existing ones, which at least our intention is that first of all, it's easier to follow what existing best practices are already there. So it's not as hard for people in smaller labs to actually follow existing best practices and evaluate on everything that they're facing pressure to evaluate on. And I think another benefit here is that people can contribute these implementations upstream to some of these centralized evaluation tools. And this gives more visibility to benchmark data sets that might not previously see as much adoption, because it's just a barrier to have to re-implement and consider all the unique factors when someone's re-implementing your data set evaluation process from scratch again.
Hi, thanks for the talk again. I was wondering what would, in your opinion, be the best way to evaluate domain-specific results? These are more generic, you can evaluate LLMs and stuff, but for your own specific problems, what's the best way to do it? We would eventually do the human evaluation, but before that, because even if you want to automate all of this, we still have to create a ground truth data set for the domain, which is also expensive. It's not cheap. So what, in your opinion, is the best way to go about this?
Yeah. So it was a little difficult to hear the whole question, but you're asking about domain-specific evaluations and considerations there?
Yeah.
Yeah. I guess somewhat underlying this is this is mostly focusing on sort of general benchmarks of intrinsic model capabilities. But yeah, if you have a specific application you want to use a model for, the best evaluation is one that's on your own data that you can sort of collect and test on, even if it's a small benchmark test set. and like that you can like have and collect and iterate on. And like, I think the closer you can get to the specific application you want to use, if there is a specific application, the easier things are, just because like a lot of these challenges arise from trying to test general systems.
Hey, thank you so much for your talk. It was great. My name is Lucas, and I lead a team at Google that's actually trying to make an IQ score for language models. So like one single like number to summarize everything. If you or really anyone else in the audience is interested in talking, please find me. But my question for you is, I'm like a little bit curious what your feelings are on these benchmarks and whether they purport to show general intelligence. Like, is MMLU supposed to be talking about all of the model's capabilities or just a small subset? And do you know of any attempts to try to make like general intelligence scores?
So yeah, I guess like there's sort of two sides of this. I think one thing is that a lot of the existing benchmarks are things that you can do very well at by memorizing your training data. Like a lot of these benchmarks sort of are testing how well you do on like factual knowledge questions. So if your pre-training data includes those facts, you're going to do better. And it's also true that things like MMLU very strongly correlate with the compute you spend on these models. So it's a little difficult to square those two facts. But I do think that if we want to make claims about I think a thing we kept trying to return to in the talk is basically like language models really challenge our intuitions about like it can do this one task. Clearly it must be able to do all of these other like supposed prerequisites. And so I think like I would hesitate to say that these are sort of assessing like general intelligence in the same way that a human faces it. But it does seem like many of these sort of do correlate with other aspects of quality in interesting ways.
So for the non-auto-recursive language models, where the perplexity and the likelihood of the tokens are going to be difficult to evaluate, what is your thoughts about the proper metrics to evaluate the non-auto-recursive language models?
So the non-autoregressive language models, and what was the specific metric?
Well, we have a bunch of metrics, but I want to hear about your thoughts. Like, is there any standards that are established in the industry, in particular for that?
Yeah, I guess like if you're talking about like BERT-like models for non-autoregressive, then I think like most people evaluate these sort of like in a fine-tuning setting, or maybe like classification on a specific task of interest. I guess like intrinsic methods for this case are, a bit more difficult to come by. Maybe we can chat after or something.
Yeah, this is true.
I just want to make sure I'm understanding this.
Thanks for the great talk, Harry from the AI Safety Institute. I was wondering to hear your thoughts on, I think it's Goddard's law. It's like when a measure becomes the target, it no longer is no longer useful as a measure. I'm benchmarked as super important, but I'd just like to hear your opinion on how that applies to your work.
Yeah, definitely. I feel like Goodhart's law is like a sort of central example of like, I think with these benchmarks that we're seeing, like the turnover rate is very, very high, and like we're just sort of applying so much pressure to optimizing for these benchmarks. And I think that like work like GSM1K looking at like these like held out private test sets and like how well models generalize to those like theoretically IID distributions is like really important work. I think that when people are releasing a new benchmark, like if they have the volume of data required, you should be holding out a private test set for a year and not telling anyone you held that out. I think like I think it's sort of like very difficult to tell what's overfitting and what's not in this era, and I think it's like a very important problem to try and tackle. I think like sort of current approaches are sort of just diagnostic and trying to figure out like what is contamination and what's not, but like it's difficult to try and tell where you draw the line, but I think it's crucially important to know we're not like overestimating performance.
Hi. At the end, you talked a bit about the limited utility of like private benchmarks or private test sets due to overfitting when it becomes public eventually. Could you expand on that a little bit? Like when I think about, for example, what Scale AI are doing now, when you're being evaluated unseen, like you don't really see the private test data, right? So is this just overfitting to the score without seeing the data, or what exactly do you have in mind?
So like Yeah, I think basically like even if the actual like labels or the inputs for a private test set are held private, like you can still sort of hill climb on it if you're allowed to say like submit to a leaderboard repeatedly until you get higher performance. And so like I think even for people who aren't explicitly getting data contamination, there's still this thing to be afraid of, which is basically like hill climbing too much until we get to the point where the proxy diverges from actual performance.
All right. So this point applies to the like general public or benchmark leaderboards. So if I'm a large enterprise and I want to evaluate public models for my private test case, and usually, Meta will not care about me, then it's less of a problem, right?
Okay. Yeah. But yeah, I think like, I think private, so private test sets aren't really like a solution to all cases here, but are definitely useful.
Thank you for the nice talk. So my question is more specific about evaluation across. So when we treat language model as a probabilistic model, right? So is it a standard practice to take multiple samples from the model and evaluate on the question? If so, like, is there any accepted number of samples in leaderboards?
Yeah. So you're asking about like running the sample through the language model multiple times. Yeah, this is definitely common practice. People will run like majority voting where you pass something through the model and have it generate an answer like k times and then take the sort of answer that appears the most in those k answers. And this is definitely like a way to get higher evaluation scores out of a model, especially if you have some sort of like reward or proxy for goodness to select the best answer, or just select like an answer that's sort of the most likely under the model's distribution, other than just doing greedy selection. That can help to like reduce variance estimates as well of benchmarks. But it is costly in terms of like running inference, which, yeah, depending on who you are, that can be a factor.
Hello. Hi. Great talk. Thank you. I would have very specific question. So, imagine a situation where you have several instances of a language model, and the answer of one instance is then proceed as an input for another language model. So you have a certain chain of agents. And would you say in this context, if this would be, for instance, a summarization task, would it be better to only evaluate the final response, or it actually does make more sense to evaluate at each stage what the agents were producing? I don't know if you understood what I mean.
So you're saying an agent use case where you have multiple different models.
Yeah, mostly so in the context, for instance, of hierarchical agglomerative summarization. So you ask across several documents. There was a paper on GraphRack recently when they were asking a high-level question about a set of documents. One approach was to use a knowledge graph and extract what was relevant. Another approach would be you have different LLMs summarizing different documents, then using those summaries to create a bigger one and then create a final. Would you say in this context would make more sense to evaluate each summary, or just the final output would suffice?
Oh, I see. So if you have like a workflow with multiple different language models doing multiple parts of a task, should you evaluate each task separately or together? I guess I think that might depend sort of which of these sort of decompositions has a better metric or a more reliable way of measuring success. So like if it's a very complex task where it's sort of the end product is harder to evaluate successfully, or like have a good metric for correctness there, then it might make more sense to evaluate each component if you can have a good metric for that separately. But otherwise, you could maybe evaluate the whole system.
Thanks for the great talk. I had a quick question. You touched on this briefly on LLMs evaluating LLM output, and you said it's not the point of this talk, but it does seem that it's kind of growing in popularity today. What are your thoughts on the matter? Do you think it's a viable strategy going forward? I mean, there are the obvious concerns that, you base LLMs on Llama 3 or something like that, and then if you use Llama 3 to also evaluate Llama 3 models, then maybe there's an inherent bias in that it kind of prefers its own output. Do you see this as being a viable option kind of in the future if we just create specific LLMs only for evaluation purposes that are maybe separate from this ecosystem of Gemini, OpenAI, Llama, those kinds of things? Or what do you think?
So So I guess, yeah, like LLM as a judge, I think is definitely like having like a huge amount of popularity. And this sort of happens overnight. I think that like more work needs to be done understanding the limitations of sort of what can be reliably judged with the language model and what can't. Because like if a language model isn't able to complete the task it's judging, then it probably can't do a great job of sort of judging correctness. Unless we maybe break it down in the appropriate way. So I think more work needs to be done understanding like the limitations here. But I think it is potentially very useful for, say, like this sort of like parsing out an answer from a model's generated text, because it's like these models are meant to operate on natural language. And so this sort of like rewriting or natural language operation is very natural. So I think in some form, like model-based metrics will definitely play a part. It remains to be seen how much or how far we can take this.
Hi, I'm curious to know if you have tried any like multi-step benchmarking, where, for example, you get text similarity. If it's, high, then you send it to a human evaluator, and then you score from that. Do you have any experience with this?
Yeah, I guess not maybe directly the exact thing you're describing. Like, I think, yeah, I guess maybe not with that direct application or use case, but it seems reasonable.
Hey, great talk. You mentioned that using n-grams or other kind of techniques to define whether or not something is zero shot or whether or not the test set has been contaminated aren't really enough anymore. And I guess, one, what are the better ways of kind of assessing test set contamination? And also, if, seeing, structurally similar or summarized text or stuff like that can mean, that the test set is contaminated. Like, what do we know what zero shot or out of distribution even means anymore? If it's not like just kind of direct contamination?
Yeah, so I guess there's two parts there. I guess first is about how to measure contamination if contamination can go beyond just like n-gram overlap. And I think the answer is we don't really know yet. There's a lot of great research that is further exploring contamination, but there's not really a like conclusive best practice that one could point to that's sort of decided here. And then the other part being what even is like sufficient distance to be counted as zero shot, and what is like generalization versus just in distribution performance. And I, again, don't think that there's a clear good answer yet. I think that this is something that's very worth exploring, and yeah, I think it should be studied.